In this video, we will tackle a vertical projectile motion problem that involves a hot air balloon. You will learn whether freefall affects objects traveling at constant velocity, that objects traveling together have the same velocity, and how to calculate the distance between two objects moving in opposite directions. Please like and subscribe, and without further delay, let's get to it. Just a note on the kinematic equations or equations of motions that we find here. Depending on your curriculum, you might use one form of the equation over another. For example, here where initial velocity is represented by vi, it is represented by u in this equation, and delta y, the change in displacement, is represented by s in this equation. Really, the equations are one and the same thing, but depending on where you are in the world or your school's curriculum, you might choose to use one form of the equation over another. Alright, having said that, let's jump straight to it. A hot air balloon is moving upward at a constant unknown speed. Is the hot air balloon in free fall? Choose from yes or no and give a reason for the answer. Well, no, it is not in free fall, and the reason for this is because it is traveling at constant velocity. Free fall refers to an object that only has gravity acting on it as a force, and therefore the object will be accelerating due to gravity and not moving at a constant velocity. So our answer is no, because the object, or the hot air balloon, is moving at constant velocity. Next question. When the balloon is 200 meters above the ground, a small stone A is dropped from the balloon. See the diagram above? So that's this diagram here. Another small stone B is dropped 5 seconds later from the balloon while the balloon is still moving upward at constant velocity. Stone A strikes the ground at a speed of 62.68 meters per second. Ignore air resistance. 3.2.1 calculates the speed of the hot air balloon. So to start off with this question, we need to choose a direction convention. This is chosen arbitrarily or at random. There's no right or wrong direction convention. In this case, I'm going to choose up as positive. To calculate the speed or velocity of the hot air balloon, we will calculate stone A's initial velocity, because stone A was traveling and thus moving with the hot air balloon. So its initial velocity, or its velocity at the instant in which it was dropped from the hot air balloon, equals the velocity of the hot air balloon, which we are being asked to calculate. Let's expand on this thought. Imagine you're seated in a car that is traveling at 10 meters per second. We already know the speed of the car, but what is your velocity? If you're stationary, in other words having a velocity of 0 meters per second, the car would move off without you, leaving you behind. But this is not the case. You're traveling in the car, and so to continue moving with the car, your velocity must equal that of the car. In conclusion, the velocity of object A equals the velocity of object B if object A is moving together with object B, because they are part of the same system. We know the final velocity of stone A, which is the 62.68 meters per second. We know that its displacement above the ground is 200 meters. And we know that stone A is actually in free fall. So once it's dropped from the hot air balloon, It is now in free fall, so we will use this equation of motion here to find the initial velocity of stone A, and stone A's initial velocity will equal the velocity of the hot air balloon. Because we've chosen up as positive, this final velocity is going to be negative because stone A is traveling down, which is the opposite direction of our chosen direction convention. So this is actually going to be negative 62.68 meters per second squared. This is going to give us our initial velocity. Our gravity is always acting downward, and because A is in free fall, the acceleration is due to gravity, and this acceleration will be 9.8 meters per second. Negative 9.8 meters per second. And our change in displacement is the 200 meters. When we simplify this, we get and upon further simplification and solving, we will find that this initial velocity is equal to 2.96 meters per second, and that its direction is 2.2. We want to know the time taken for stone A to strike the ground. Well, we know stone A's acceleration, we know its final and initial velocities, so we can use this equation of motion to calculate the time it takes stone A to strike the ground. Our final velocity is this negative 62.68 meters per second. Our initial velocity is the velocity that we calculated in the previous question of 2.96 meters per second. And this is going to be positive because stone A was traveling upward at its initial, before it was dropped. Stone A was traveling upwards before it was dropped, and because we chose up as positive, this initial velocity is going to be positive. Gravity is negative because it always acts downwards, and it is opposite to the positive direction which we chose. And time. So simplifying algebraically and solving for time, we get time equals to 6.7 seconds. Alright, final question. We're asked to calculate the distance between the hot air balloon and stone B at the instant when stone A strikes the ground. So for this question, I'll draw a diagram just to quickly illustrate what is happening. If we take this as the ground, we know that stone A strikes the ground here at time t equals 6.7 seconds. Right, this is what we calculated in the previous question. The hot air balloon continues moving upwards at constant velocity, right, after stone A has been dropped from the hot air balloon. Hot air balloon will continue moving upwards. 5 seconds after stone A is dropped. So this was given in the problem statement. 5 seconds after stone A is being dropped, stone B was dropped from the hot air balloon. So this represents stone B. It was dropped from the hot air balloon 5 seconds after stone A has been dropped. But this time here, right, where stone B is, this distance above the ground, which we still have to calculate for the question, this time here is going to be 6.7 seconds, right? 6.7 being the time it takes stone A to reach the ground, and it's going to be minus the 5 seconds, which represents the 5 seconds that after stone A has been dropped from the hot air balloon, that stone B is now also dropped from the hot air balloon. And it's at this point above the ground, it's this displacement above the ground for stone B that we're looking to calculate. This time here is going to be 1.7 seconds, and we're going to use this in our calculation. If we start then with our hot air balloon, we will be using this equation of motion over here, delta y equals vi delta t plus a half a delta t squared. Now this part of the equation will evaluate to 0 because the hot air balloon is moving at constant velocity, and therefore it does not have an acceleration. Its acceleration is 0. Substituting into the equation, the initial velocity of the hot air balloon is what we calculated up here, and it was 2.9 meters per second, 2.96 meters per second, and the time is the same time as for stone B, this 1.7 seconds. And we should get an answer of 5.03 meters. So just a note on this 1.7 seconds, this time is the time that it takes stone B to reach this unknown height, or still to be calculated height above the ground, after it has been dropped from the hot air balloon, and also at the instant in which stone A strikes the ground. So that's what this 1.7 seconds represents. So continuing the calculations, this time for stone B, we will use the exact same equation of motion, delta y equals to vi delta t plus a half a delta t squared. Stone B's initial velocity equals the hot air balloon's velocity because it was dropped from the hot air balloon. So this is positive 2.96 meters per second. Our change in time is the 1.7 seconds, which we've calculated, plus a half. Well, now stone B is traveling downwards, so its acceleration due to gravity will be negative because we right at the beginning chose up to be positive. So this is going to be negative 9.8 meters per second squared, and our change in time, which is 1.7 seconds squared. Plugging this into the calculator, we get negative 9.13 meters. Now B's displacement is negative because it is moving down, right? Stone B is moving downwards, whereas the hot air balloon's displacement is positive because it's moving upwards, and we had initially chosen up to be the positive direction. So if the motion of the object is opposite to the direction convention, then its displacement will be negative. Now to calculate the distance between the hot air balloon and stone B, which is what is being asked of us in the question, is this distance here. We will just take this at 5.03 meters. And we will add this 9.13 meters. Or rather, we can subtract. So minus 9.13, which is effectively adding, so 5.03, because a negative and a negative will make a positive, plus 9.13, and this will give us 14.16 meters. This 14.16 meters is this distance here between the hot air balloon and stone B at the instance where stone A strikes the ground. Just a small note on this. Remember, the hot air balloon started at 200 meters above the ground. Right? If this is 200 meters above the ground, the hot air balloon then traveled up this 5.03 meters. So this distance here is 5.03 meters, and stone B traveled down 9.13 meters. And it's negative because stone B is traveling down, which is opposite to our direction convention. So it's, in essence, it's negative 9.13 meters. But this total distance here would be this 5.03 plus our 9.13 meters, and that will give us a total of 14.16 meters. That's the distance between stone B and the hot air balloon at the instant when stone A strikes the ground. I hope you found this video helpful. If you have any queries, comments, or concerns, please feel free to mention them in the comments. In this video, we solved a vertical projectile motion question involving a hot air balloon. You learned that an object traveling at constant velocity is not a projectile and thus is not moving under freefall. You also learned that the velocity of object A equals that of object B if both objects are moving together. And lastly, you learned how to calculate the distance between two objects moving in the opposite direction to each other. Until the next video, subscribe.